of people, both physics and chemistry and biology, working on that, even geochemistry. I got a mail from yesterday from university abroad trying to reproduce some of our work, and that person is from geochemistry. It's very interesting that and such is going on for now almost 30, 40 or 50 years. And okay, now why is so much interest? So some time ago, I gave a similar talk, which is made by one of my students. In Bangalore city, they had a they have a science organization which had this talk in the city. They call it Submart. So I gave a talk there, which was also very disorganized. So I think it's organizing a talk has to be certain amount of professionalism. Okay, now.
Sorry to
I cannot hear.
for my
I cannot hear you. Bolo.
Sir, we have to formally introduce you before.
No, nothing. It already is enough late. Okay, now no problem. Now let me start. Don't stop me, huh? I hope students are there. Anybody can look at me and Google. And I don't want. It is only 10 minutes late. So please forget it and don't stop me. Okay. So water is, as I said, is a fascinating liquid, and we in Bengali and many other languages we say it's simple like water, and as I said, it is, if anything, water is not simple at all, and it's a wonderful subject to study. As I was telling you, very large number of physicists, of course, physical chemists, who can claim the A to it, geologists, biochemists are working on that. So now, the title is Water, Water Everywhere, which was a changed slide, but it is because this famous line of Rhyme of the Ancient Mariner, Coleridge, Samuel Coleridge. So Rhyme of the Ancient Mariner, there is this line, water, water everywhere, not a drop to drink. So it is really fascinating. People take a lot of pictures and these beautiful waves you see. And I think 3 years ago, I went to Sundarban, and they took us in our steamer to a confluence of 5 rivers. If you have not gone, go there. It's so beautiful. You have water everywhere, and almost like ocean. But whatever, the tremendous fascination that we have in water is originally basically because we came from water. However, and water is a tremendously important material. But we have really neglected studying water, but that has been more or less, because usually there is water's problem is that both in chemistry and biology it is abundant. So it's kind of play a hidden role, and a human mind is that when something you get easily, you don't value it. You go after chips and some other things, materials, science. But I'm not saying you should not study them, but this is just amazingly fascinating subject. So from ancient times in Indian culture, we do have the place of water from ancient times. That is just like this one, Rig Veda 10:9, water is your health giving, give us energy. Then like mothers longing with love, so gladly do we go wherever is water we go. Remember the Nile River, or every civilization, and civilization died whenever water was available. Give us progeny, gaseous, be divine waters, bliss and happiness. That's true. Water bring you happiness, as I was just saying. Tremendous happiness it can bring. So this is, of course, one of the major things of our. And this is something all of which function we start by giving this offering. The Gange cha, Yamune cha, Saraswati, Narmade Sindhu, Godavari, Saraswati, Narmade Sindhu, Kaveri, Jalismin Sandivini Kuru. The holy rivers Ganga, Yamuna, and also Godavari and Saraswati, and rivers Narmada, Sindhu. It covered all the rivers of India. Kaveri, please be present in this water and make it holy. That is a very common way we do offering that you do in your functions, religious functions. So much beauty of water, so much uniqueness of water. What makes it so unique? Answer people have asked, and most of the time people didn't have any answers. People went to philosophy, and it took very long time to understand. Probably first understanding of water came in 1970, around 1970, when two very smart scientists, one of them is had he lived, would have got certainly the Nobel Prize, Anisur Rahman from Hyderabad, our Hyderabad here, and Frank Stillinger. So they simulated water for the first time in computer simulation, and they found amazing properties. That was essentially could be called the beginning of our modern understanding. 1970. History is very important. Now, so questions are that what are the unusual properties of water? What makes it so unique? So unusual and universal. Then how does it move? What are its dynamics? A water molecule or a collection of water molecules. Then water surfaces is a hugely important thing because we have water in nature, in surfaces, and in confinement. Remember that your fruits and even tissues in trees, they are about 70-80% of water. Your human body is 70% of water. So there is a big question that's given in red now is very important, interesting, and very important now. Many nature science are getting published on this. How did the effect of surface penetrates into water? This is a very important question. Then there is a lot of, because it's very relevant to also biology. So hydrophobic force law from proteins to hydrophobic surfaces. Huge number of questions from many different sides that comes for water. So now there are some basic facts. What is a small size, small molecular weight? Its hydrogen bond forming ability. I'll go through all of them very detailed because the talk is somewhat for the undergraduate students. Hydrogen bond forming ability, it can form 4 hydrogen bonds. And that's very unique. This number 4 also plays a very important role. And not only it's a 4, it has a tetrahedral geometry. So it's a nonlinear molecule, which allows it to extend its structures. What is, when it comes to a protein surface or DNA surface, it can act both as hydrogen bond donor and hydrogen bond acceptor. So it can bind both to a positive charge and to a negative charge. Remember, oxygen has a charge of minus 0.8 and 2 hydrogens are charged plus 0.4 plus 5. It's a neutral molecule. But because of this, it's such a small molecule, then it is somewhat polarizable with oxygen to lone pairs of electrons. So this is a unique, to the extent, search for life in anywhere extraterrestrial starts with the search for water. However, we say, but probably we have not figured out in a way how life can survive without water. And so the uniqueness of water are in these 5. I have a book where I have given 6 unusual characteristics. When I was writing this, I remembered 5, my own book. I'll show you the book and I'll send you the book to the college to be forwarded to students. Now, the plan of the talk then is the structure of water, It all little bit. I'll talk more of that. And then anomalies of water, I already talked. We'll talk a little bit of freezing of water and melting of ice. It'll be wonderful, please. We'll talk of motion of molecules in water. We'll talk a little bit of solvation of small molecules in water. Electrochemistry, water is many times the main thing. And so we have this beautiful picture of Manashwar over here. I believe so. Yeah, that's probably. Now here, the structure of liquid water is that I said 1 oxygen, 2 hydrogen. It should be delta minus and 2 delta plus, or that means there is equality. The delta minus is 0.8. It's not small, it's pretty large. Oxygen has a pretty large charge, 0.8 for a neutral molecule. And these 2 hydrogens are placed symmetrically with a charge 0.4. So because of this charge, plus and minus, there is a weak electrostatic interaction, which under certain conditions are called hydrogen bond. And this tetrahedral, as I am showing on the right side, the tetrahedral, the arrow shows. Okay. These bonds continuously form and break in liquid water. And the order of 2 to 3 picoseconds. This is a very, very short lifetime. So it's a simple molecule, as I said, it's a very, very simple molecule. But it's a very complex liquid. So I will continue this theme that small size is an extremely important issue in my list of very small size and small molecular weight. They are very important. It can move really very fast. Then formation of hydrogen bond I already discussed. The partial charges, but the molecule is unique. Molecule is neutral with a dipole moment which 1.85 dBi, which is neither too large nor too small. For a small molecule, it's little large, small neutral molecule, and but it is now this hydrogen bond. I discussed is the bond between a hydrogen oxide, certain angle and certain distances was advanced in the theory of Linus Pauling, which he extensively used it. And he found that this bond that we are calling hydrogen bond is actually 5% covalent bond. Rest is electrostatic. And Pauling made extensive use of the hydrogen bond, and he realized very early that it is the hydrogen bond that plays such an important role in biology, in structure of proteins, in structure of DNA, of course, duplex is held together by hydrogen bond. So that commencing in, so I'll have this Linus Pauling probably back again. So unit is continuing. I said it's formed. It can be both hydrogen bond acceptor and hydrogen bond donor, can stabilize both positive and negative charges. Transfer electron density from oxygen atom of the acceptor molecule to the hydrogen atom of the donor. So this has a high melting and boiling point for such a small, tiny little molecule. It has a very large boiling point, 100 degrees centigrade. And you see, small molecules like that, they actually hardly ever liquid. And if they're liquid, you have to go to minus maybe 100 degree centigrade to make it a liquid. But not like, remember nitrogen. Nitrogen, you have to go, I think, some 176 K. Yes, minus 100 degrees centigrade. So it's a very, very, but water is not like that. Water, nitrogen is heavier than water. But water is, that's why we survive, because this 100 degrees centigrade range we get from 0 degrees centigrade, which is the melting, to boiling, 0 degree to 100 degrees centigrade. That 100 degrees centigrade range is extremely crucial. So because of this tetrahedral geometry, hydrogen can form an extensive network. And that extensive network can be 4 hydrogen bond, but each water molecule can be 4 coordinated. It can be 3 coordinated, and I have shown here some pictures where it is 4 coordinated. Remember, in ice, water is 4 coordinated. That's very important to remember. Ice is we call it hexagonal ice, ice 1H. There are other forms of ice. I'll show some of them. So, when we call it is 4 coordinated, then the nomenclature loosely used in liquid, but more firmly in ice is that it's expected to be 4 coordinated, hexagonal. But when it's 3 or 4 coordinated, they are present. It's not that they are not present. They're very small quantities. And before melting, these 3 coordinated species plays very important. And in dynamics of water, the interconversion between 4, 3, and 5 play very important. Okay, now there is a simulation of water. I don't know whether it's made by my student or taken from YouTube. Could be. But you can see now is a little flow, of course, so that everybody can see it, that how water molecules are moving around. Now, these thin lines which you are seeing are essentially these electrostatic interactions. When they come close, we call it hydrogen bond. But they always have certain attraction. And because of that attraction, focus on any one of them. Because of that attraction, you get the rigidity of water, the high melting point and boiling point, and the viscosity of water. Viscosity is 1 centipoise, which is very large for such a low molecular weight. You know, water, if not for this uniqueness, it would have been gas with a probably viscosity of something like 0.2 centipoise. Remember, astronaut which is so much bigger, is viscosity is 0.39 or say 0.4 centipoise. But water is, but basically this what you are seeing in front of you is a caricature. It's a model. We don't see them. Even now, you cannot see them in water molecules moving. But this is what you believe it is. It's very interesting that this tiny little molecule, we believe is what it is doing here. What you're seeing in front of you is a water molecule. With what you drink, the molecules behaving like that. There are many fascinating things that, okay. So basically, continuing with the uniqueness, that the hydrogen bond that we see here, which is that it is continuously moving, and that is the fluctuating hydrogen bond network. Each structure of this hydrogen bond is marginally stable. There are many such arrangements that are possible. Each marginally stable. There is a way to freeze them in computer and then find the energy and find the kind of it. You find that when you do that, a number of molecule water configurations can be mapped into one minimum. We call that basin. But one basin is separated by another basin by a very small free energy barrier. So molecules are continuously moving, highly dynamic things. There are many anomalies like a dipole moment, not too large, 1.8 device, okay, but it has, compared to dipole moment, a huge dielectric constant. And you know, dielectric constant is a very important property. It's a screening constant. It screens electrostatic interactions. And that plays a very important role in electrochemistry and reactions. This dielectric constant of 80. And dielectric constant of 80 is we kind of understood on in last 10-15 years that why dielectric constant is so large. Okay, and there's a cartoon. The student who made Showmok, he makes all these beautiful cartoons. Here, sodium and chlorine. Is the sodium and chlorine are very happy, but when you put them water, you know, water solvates, and as a result of that, now their interaction, positively charged sodium, negatively charged chlorine, chloride ion, they would like to come together, but their interaction between them is screened by the large dielectric constant. The water solvates each of them. So once you put a sodium chloride, molecules just dissociate and they go far from each other. It's a very nice cartoon. So now, water has got several isoenergetic structures, both liquid and solid phases. In liquid, there are two structures which are very, very important and has done huge amount of work. It's called high density liquid. The liquid that we drink, that in our room temperature, is called high density liquid, HDL. When you go to lower temperature, it goes to a lower temperature liquid called LDL, low density liquid, which are certain characteristics of ice. Now, ice itself is a amazing variety of structures depending on pressure and temperature. The 18th ice structure have been kind of confirmed. Even now and then one nature and science paper comes with one more ice structure. So the ice 1H, that the one in your refrigerator and you're putting on your food, is the one hexagonal ice. It is very close in stability to cubic ice, which is ice 1C. But then under pressure and different temperature, you can get, I have not shown the phase diagram, you can get ice 12. And see the beauty in ice 12, it has it is one of the phase, 5 coordinated, large number of 5 coordinated rings. And here in the ice 2, it has both 5 coordinate and 4 coordinate rings. First time I went to a group which works completely on ice, and the students, all the students have on their table all different structures of ice. I was a bit surprised then because I didn't know all the what I knew, of course, ice is polymorphic, but the that it can be so fascinating, that took me quite some time to understand. Okay, so what are other anomalies? Macroscopic anomalies. It has a large. We have a density maximum at 4 degrees centigrade. It has a large specific heat. In addition to large viscosity, it has a very large specific heat, and that will bring in some very nice physics for students. It has large isothermal compressibility. Then anomalous thermal every property is just fascinatingly different. And if you please ask me later, if I don't get to it, why? What is explanation for some of these things, which we now understand. Here is the 4 density maximum, which you have known class 8th grade, that water has density maximum at 4 degrees centigrade, which is our standard, by the way. When you say density 1 gram per cc, that comes from there. And then some density in the solid state is about 10-11% lower in ice. And so it forms this glaciers float. And it has very important role in marine life. And now it's extremely important in global water conservation. But some of these ice glaciers, they float, they're huge. They're huge. And you know already from Titanic movie, they're only 10% is up and 90% is below. And they're just huge. That's one of the things to what's seeing. And in marine life, it helps because very low temperature, which is the right hand side here, the marine life go low, where temperature is large. Highest density settle at the low, the 4 degrees centigrade. And on the other hand, in a high summer, marine life goes somewhat below to escape from the heat. So this is what the specific heat. I'll explain this to little bit, this specific heat and the compressibility, the physics behind it for the students. The specific heat is this 1 over kVt square delta H square. This is the specific heat. And look at that. Normal typical liquid, when you go to 0 temperature, the specific heat at constant pressure goes to 0. But no, water ultimately goes to 0. But in between, it really goes up. It reaches a pretty large value. Now, same with compressibility. Now, look at the equations I've written here. That specific heat is mean square enthalpy. Compressibility is mean square volume fluctuation. So, a liquid is continuously undergoing fluctuation, as I told you, from one configuration to another configuration. And that is the reason for all these anomalies, that it has many isoenergetic structures, slightly different, not completely isoenergetic, and it is completely going from one configuration to another configuration. Now, as you go to lower temperature, most of the liquid, these energies difference become less, and the transition from one configuration to another configuration becomes less important. But in case of water, it becomes more important. The reason is that water has these two forms. One is high density liquid and this low density liquid. Low density liquid comes at around 228, let's say 230 Kelvin, minus 45 to minus 47 degrees centigrade. That is where, if you can study it, you see water undergoes an explosive crystallization just below that. But before it goes to crystallization, it undergoes a low density liquid, which is density of water. If 1, then that is 0.9. And ice is about 0.9. So this low density liquid, however, even when I have an HDL, then our normal liquid, we have this binary mixture. That means there is certain pockets of low density liquid which is higher free energy, but not that high that it will not influence the property. So there are kind of a seesaw going on continuously, and that is giving rise to large fluctuations. Now, a few basics I want to teach the. So how do you understand these things? How do you understand this specifically divergence? How do you understand becomes very large? Isothermal compressibility becomes very large. With any material, how do you understand them? You understand them by doing statistical mechanics. So what is statistical mechanics? This is 3-4 transparencies I try to show to students. Most of my talks, I very recently gave talk to St. Stephen's, and I also again taught a little bit more what I'm doing here than I did there, because the talk was not just water, it was more or less a physical chemistry talk. But now the statistical mechanics is, now look at the name, mechanics and statistics. The mechanics is very deterministic, there's nothing statistics about it. But then statistical mechanics is when you are incorporating statistical principles into mechanics. That is statistical mechanics. Why you need them? Because I have a book, please, free lecture series done by NPTEL, available on YouTube and internet, where I taught statistical mechanics. You can call statistical mechanics 1, basics of statistical mechanics, or basic statistical mechanics. Very important thing is that when you start from, and I have a book which is given here. Someday if I go, I'll give a copy to library, to a library, except that I have left only one copy left. But I can buy one and give you to library, because it's a good book. Now, so when you start from to understand the properties like this specific heat, isothermal compressibility, viscosity, conductivity, all the properties of water, you need statistical mechanics. The basic idea is that molecules interact. I told you electrostatic interactions, hydrogen bond. So starting from those interactions, how do you go to observe properties? And that is where you have to use some statistical concepts. This was developed by the several great thinkers. It all started in Maxwell. James Clerk Maxwell formulated the Maxwell distribution, and that Maxwell's paper fascinated Ludwig Boltzmann, who is called the father of statistical mechanics. And it's really interesting. Sometimes the title goes to Willard Gibbs, but probably both deserve the title. Ludwig Boltzmann first tried in a very hard way to go from mechanics, from Newton's law and interactions. So two water molecules come close to each other, they interact, they exchange momentum and energy. Then another water molecule joins it. Think of this building all the huge Avogadro number of water molecules. Ludwig Boltzmann, brilliant person, he had the hope that he would be able to use Newton's equation, laws of motion with the intermolecular potential and through collisions to develop the whole field. He didn't succeed, but in the process, he developed many, many beautiful things, including he introduced essentially what is the microscopic definition of entropy. And that is what is the part of statistical mechanics. The entropy is KBL in omega. Omega is number of configurations. So I was talking with water has all these configurations going from one to the other. Entropy is determined by the number of configurations, number of accessible configurations. Now, then on the other side of the Atlantic, Willard Gibbs, bachelor man, all his life, he's the Yale University. He just worked, created many things, and one of them is equilibrium statistical mechanics. He realized very from the difficulty Boltzmann faced. Boltzmann, there is certain on that, controversy on that, but whether he committed suicide or he fell in river and died. But he was a frustrated man. But from the difficulty of Boltzmann, Willard Gibbs realized that he took all from Maxwell and Boltzmann. But he realized that way of going through Newton's law is far too difficult. So instead, he had a brilliant concept, which is called ensemble, which I'm not going to read. It's described in my book. But he introduced the concept of ensemble and brought in statistics in a much more rigorous and vigorous way into describing. And then he was able to he introduced a quantity called partition function, which is defined in terms of intermolecular potential. You must have heard of Hamiltonian. So partition function is integral over that Boltzmann factor of the Hamiltonian. So Hamiltonian is energy. So e to the power minus beta. Beta is kb 1 over kbt. So e to the power minus beta h. And the integration over that is the partition function. Then that allows you to calculate the specific heat, allows you to calculate the entropy, calculate equation of state. You can now derive in a much more detail in van der Waals. Actually, I should pay probably more respect to van der Waals, because without doing statistical mechanics, van der Waals was extremely successful in taking into account intermolecular interactions, the attractive and the repulsive part. Okay, so then postulates of statistical mechanics, there are two postulates. One is the first postulate, what is the time average, and that equals the ensemble average. And another is the second postulate, equilibrium probability. So Boltzmann tried to do this time averaging. That was his thing. But Willard Gibbs realized that this cannot be done. I cannot calculate a property over a very long time that is given by T equal to infinity. I cannot do that because I cannot solve Newton's equation for Avogadro number of particles. That's nobody can do. Even with computer, we cannot do it now. We can do 1,000, 2,000, maybe 10,000. But that's most of the time is enough, except near the phase transition. And that's why the picture of ensemble was introduced. But then the second postulate is the equal a priori probability. That means all microscopic states are equally probable because the system is going from one to the other at constant energy. So then one introduced the probability concept, that probability of finding any state is 1 over total number of states. So this was the statistical mechanics. Time average was done by Boltzmann, and ensemble average was done by Willard Gibbs. Then the postulate and the ergodic hypothesis. Ergodic hypothesis was already there, and this was the so it is very interesting. Statistical mechanics is a huge area, and it is based on only two postulates and one hypothesis. That's it. Amazingly beautiful subject. Now enters the master, the fluctuations and response functions and Brownian diffusion. So, but it just, sometimes you just wonder how one man. Actually, what I said about Mahatma Gandhi, that in years to come, people scarcely believe that such a man in flesh and blood ever walked on the surface of Earth. I think to some extent that also goes for only Einstein also. That time there was a famous experiment by Robert Brown, who looked into the pollens, many different kinds of pollens on suspended on surface of water, and he found on a microscope, then optical microscopes are quite powerful, that these pollens are continuously moving. He was really puzzled. First he thought, of course, the pollens are alive, but then he found dry leaves of many different things. He always moving, these pollens and all different kinds of moving. So he realized that it is some inherent property of the liquid, that the liquid is atoms and molecules must be in motion. So Einstein really formulated that concept beautifully by introducing many equations, that two are given on the right hand side, that he said. He also did that mean square energy fluctuation and delta H square, you can specify it. That is Einstein. Delta H square Cp, that is Einstein. But main thing here, that is equilibrium fluctuations. Here is a dynamic fluctuation. I show a trajectory. And that along the trajectory, energy is moving, and that's the specific heat. But atoms and molecules are moving. And that is giving the diffusion. And diffusion is how much a particle is moving, rate of moving of the particle, that diffusion. But then he derived this beautiful relation. Diffusion is cavity by friction, and friction is related to viscosity. So one gets many beautiful relations from statistical mechanics of diffusion, viscosity, chemical reaction kinetics, and many things. So then thermal expansion, another very funny property of water. Okay, so I told you some of the anomalies, that the freezing temperature motion of molecule become increasingly slower and correlated, and the specific heat. So there are all these kinds, not just in supercooled liquid, normal liquid, the water has. And as I told you, only recently we have begun to understand it in terms of hydrogen bond, because in terms of network structure formation, which is so different from any other liquid. Neither in acetylene nor in methanol or ethanol, you have this kind of the things. So here is a small molecule who is the protagonist in our today's discussion. That small molecules is doing a huge amount of things. Okay, so now I'll show you certain interesting things of freezing of water and melting of ice. So as we know that it forms a beautiful ice forms, and snowflakes, and these are everyday phenomena. You see it every day. But you hardly stop to wonder how it is happening. That all these things that we have in our eyes is a small molecule is the player, which is not only 70% of your body, but also allowing you to digest your food. Whole of biochemistry would not have been there in our body without water. And but in addition to your body and your refrigerator, in nature, it is a dominant force. It is the mover and shaker of many things in this world. Just yesterday, the sad thing, you saw this huge flood in Germany and Switzerland and all these places. And few days before that, we had a flood in India, again in Uttarakhand. But you can see them. I remember first time I really realized the blind force of nature when I was in 1 month of October or so. October, November, I was early October, huge rain, and there's a flood in UP. I was going to Kanpur IIT, and I was looking forward to cross. I always look forward to crossing that bridge over Ganges. And then I saw something such a spectacle that usually half dry riverbed, it's just disappeared. Huge amount of water flowing in a really amazing speed. You know, we have a famous novel called Srikanto by Sharachandra Chattopadhyay. And there he describes in one place these two boys went to catch fish. And that's where Sharachandra had an amazing description of water flowing in a water season. Water is flowing in a huge speed. But you know, Sharachandra tried very hard and captured some of it, but I never realized what could be a rapidly moving water. And it was flood situation, water's coming down from Himalayas and upper plains, huge, and there are big trees rolling in, there are big boulders rolling in. So I stopped the car and I came out of the car and stood on the bridge, and then security men came running. They said, no, you cannot stop here and you cannot just move. So I moved. Then after going there, I told that I just want to go back to bridge. I alone, not the car, because I want to see this thing. Then they, after some hesitation, I told them to come to car. Right? They allowed me, and I went to it, stood on the bridge. Just amazing. I then realized, God, that's how people flood. That is what flood does to you. That's why people die so easily. So here is now, we are going to do freezing of water. So water on the right hand side is the random water, moving very fast, depending, of course, what's your camera speed. And on the left, I'm showing you how ice is forming. So right hand side is a molecular view at a microscopic length scale, formation of 6-member ring. On the left, you see the ice forming. So ice was seeded by small water and from ice cubicle or icicle, and then it's through the see the 6-member rings, and all those that sticks are the hydrogen bond. And so this is on the again this on the left showing, and this molecular view here. Lepton one started a little earlier. This is actually done by my friend, Professor Yaomine, very good friend of mine. When he was, this is a nature paper, very famous paper. And so these are movies from his lab. So how does water freeze? Really very interesting. It's very difficult to freeze water because water is perpetually moving. It does not want to static. So there is a small region where hexagonal long-lived hydrogen bonds form. This is a very interesting molecular view of how a solid forms, a very difficult solid forms. And then that stabilizes. Now the initial nucleus that forms is disorder. So two things happen at the same time. It becomes stabilized. At the same time, its surroundings also become ice-like. So two things must go together. That is the difficulty of freezing. That's why water, pure water, does not freeze till -4 degrees centigrade. When it freezes, because you have impurity or you have icicle. But otherwise, water does not freeze, pure water. It's called supercooled water. And that's extremely important, that the reluctance of water to freeze plays a very important role in many natural, protecting marine life, protecting trees. Now, also melting of ice from the same lab. Now you can see this ice on the left is melting, and so it is now the ice. Then look on the left corner, a 3-membered ring forms, and the 3-membered ring A three-coordinate hydrogen bond is the one that has to be stabilized and then propagated. So this is the melting. That's how melting. Look at that on the left. There is. Okay. So how does ice melt? I described how it and then it gives a special separate defect pair forms. One 3 coordinated and another 5 coordinated. But just forming is not enough. They have to get separated. And not only they have to be separated, they have to be separately stabilized. And that's why we call entanglement. There's a paper, there's both a nature paper. One is 2002 and there's 2013. Melting and freezing was 2002 and melting is 2013. Okay, now we do something which is more chemistry or you can say chemical dynamics. So one thing is that in what role it plays in biology, why it is so important in biology, and what's the role? This was again, it took a very long time to get any basic understanding. I just had a meeting in Telluride in the United States, online virtual meeting, exactly on this water in structure dynamics and in biology 2 weeks ago. Fascinating conference. So we had a really lot of fun. They're small, they are about some 30 speakers, mostly speakers and some students, but not a very large number, not a large number of students. So is a Telluride is a place in Colorado, a mountain town, beautiful mountain town. I was lucky there, but only once. Many people go many more times, but I never went, but only once I went. But this time it's a virtual conference. It's amazing the kind of work people are doing. But we are fortunate to do one work. In 1997, out of nowhere, we did that work. We call that biological water. And I'll talk a little bit of that. And that now is such a big thing. So that's why they invited me to give the first talk. And it was very interesting. Though most of the scientists were younger, quite a bit younger than me. But it was a lot of fun. Now, so I'll now talk a little bit of that application side of water. Okay. Water, as I said, huge amount of anomalies. One of them is the ionic mobility. See, most of the time when you place on here in this left panel picture, please look at carefully. I plotted the conductivity. There's undergraduate physical chemistry called Walden's product, made it so uninteresting. Whether Moore or Castellan probably slightly better than Moore, Glaston, they make it so boring. So what it is said is that when you multiply the limiting ionic conductivity, which is nothing but diffusion, by the viscosity, then what is left on the right hand side in the Stokes-Einstein equation is 1 over size. So then if that picture is valid, then if I plot it at 1 over r ion size, then it should be a straight line, like it should go like this. But it is not going. By calcium or rubidium, it turns cesium, it turns around, not calcium, sorry, cesium, rubidium, it turns around, and then it just goes down. Same everywhere, but for much more sharp in water. And again, another anomaly for large ions also, one sees that a breakdown of dependence on size, same size, but completely different ion. Okay. Now, how do you understand that? How do you understand this fact that that ionic mobility, again, water behaves completely different. It's dramatically different from other things. So in order to know that and know many other properties of water, we need to understand how the water molecules move. What is the dynamics? But how do you understand dynamics when the dynamics is in picosecond time scale, 1 picosecond 10 to the minus 12 second? How do I understand it? I told you we cannot see it in microscope. Only way to not quote unquote see or study is through spectroscopy. And that is what people did starting in 1990s. They shine light on that, excite a molecule. They placed a dye molecule, excite it, and they see that how the energy of that dye molecule, because dye molecule is they are fluorescing, how the frequency shift, that they could measure. And that happened extremely fast time scale. But then one has to disentangle things from that. That is one really amazing thing. Water is so fast. And that fastness, or the nimbleness of water, plays an essential role. Water is really nimble. Okay. So when I created an ion or I move an ion, then many things happen in surrounding these are water molecules. The arrows are a caricature of water molecules, and plus in a sodium ion. It moves a little, but water molecules all need to move. Then there's a nitrate ion. If nitrate rotates, all water molecules have to allow that. This is a very, very important thing. Water molecules very deeply participates. It solvates and almost drives many, many things. It's kind of scary, the magnitude of its involvement. So this is one place where you can get the solvation. Solvation dynamics. You can get that. So the experiment I was telling, this is actually very interesting history. This is written in front of me by drawn in front of me, the right panel by Ahmed Zuel himself. And you can see the spectroscopist. He's exciting the extreme violet light and violet, blue, green. So when they exciting, the energy gap between ground state and excited state is large, so high frequency light. But then the system starts relaxing. The system is ion or diplomat and the water molecules. So when I excite, look at the left corner of the right panel. When I excite, it goes over to a higher energy state. Solvent molecules, water molecules have not moved, but now water molecules start solvating. Water molecule is happy because now it can solvate the ion or dipole, and it comes down. So it's a beautiful picture, and so one now spectroscopically can measure how long it takes. And it turned out it takes very little. Water does this kind of experiment one does only in less than a picosecond. Actually, first part, 70% is only 100 femtosecond. Amazing. This really, how do you understand that? Okay, long time ago, we derived an equation microscopically, but this equation, this shift that happens, that means relaxing from this gap minus the maximum gap minus the minimum gap is called delta nu, which is shown on the right corner of the right panel. Energy coming down. The total shift is delta nu. This is this quantity. So you it depends on the many things, but one of the important thing, it depends on the dielectric constant, which is epsilon naught shown here. Okay, so the guy who measured it was by Graham Fleming and his group, and that's in this molecule coumarin. They excited the coumarin, so this thing, they excited the coumarin, the right hand panel, that experiment they did optically, and then look at this and found out the time it takes and plotted it in a kind of measured shift. That is shifting, the spectrum is shifting, and the ST is this time dependence of the spectrum shift is ST. And look at that initial thing. Look at your axis, picosecond, 0.5 picosecond. So a huge amount is done within 0.1 picosecond. And 0.1 picosecond is 100 femtosecond. And then there is a slow component. These are understood experiment, both experimental and theoretically. But this is a hugely interesting thing. Now, before these experiments, both Amit Zuel, Graham Fleming, even Rudy Marcus, the great other Nobel laureate, wrote papers, several papers on that. There was a very nice, we know all Unsagar, the great scientist. Unsagar made a comment in a Banff conference in Canada and near, I think, Toronto, that people are asking how would be the people didn't know anything in 1976. So there were a lot of argument how will water structure itself and what will be time scale, how it will happen. Nothing was known. And so Onsaga made an interesting comment. Onsaga said the polarization structure of water will be like snowball. But it is inverse snowball. That means structure will build from outside in. So that means when you create an electron or create an ion, then the water molecules that are far will be formed fast. Their polarization structure, their orientation structure, their arrangement will be done fast. So far from the ion will be then it will be built inside. Very, very interesting. And this is called Onsager inverse snowball picture, which really triggered a lot of work in this field. Fascinating thing. And dielectric relaxation is in the aqueous protein solution done. And they show this kind of non-exponential things. And people started now looking all different kinds of things. They are trying to understand dielectric relaxation of protein, dielectric relaxation of proteins, aqueous protein solution, aqueous DNA solution, a lipid, many things people have started doing. And they're all very, and this is one of the early papers showing that really a multiple structure. It is not single exponential. It has many time scales as I'm plotting the dielectric frequency dependent of dielectric constant again frequency. If it was only one, then I would have just got something like coming out like that. 1 over frequency square. No, it decays, then is the plateau, then again decay. So this is in aqueous microprotein solution. Things have been done for other protein solution also. The very active area of research. And when one say, okay, in order to understand that, let me understand the protein. How does protein rotates? And then one does a protein rotation. And then one uses the friction. This is a Stokes-Einstein kind of idea. We don't have time to go through that. But one finds that a protein is not alone. When protein rotates, it rotates with water molecules with it. So if you do take this Einstein's equation, Stokes-Einstein's equation, with the crystallography radius, you get a rotation of 14 nanoseconds. But the experiment gives a 45 nanoseconds. The factor of 3 was a rigid hydration layer and all the kind of things, like almost like snowball. They're almost like your iceberg model that you have in Castellan and Moore in undergraduate to explain the breakdown of Halden's product. Very similar thing. So Utrecht then did the next experiment. Another Nobel laureate, the person who got the Nobel laureate because of getting the structure of mad cow disease, and many other things. Kurt Utrecht. And he said, okay, it is not iceberg. It is not like a rigid ice around protein. It is moving and staying, a water molecule staying less than 300 picosecond. Then there's a lot of controversy. Another very famous Swedish scientist, he said, oh, it is just a few picosecond. So that is, here is again, I go back to, again, kind of Einstein, that he is showing what is the diffusion of molecules. That it is, solvent we have made dark, but the TAC molecule, which is moving, would be an ion or a protein or a dye. that is moving around. This is called Brownian diffusion, the same thing Einstein did. But the relation, how fast it is moving, is dependent by the viscosity. These are very, very interconnected. So it's a field where physics, chemistry, mathematics, because random walk is a stochastic process called random walk. This is a huge area of mathematics research. And this kind of stochastic equations are very much studied in mathematics. Okay, so in I was telling you that some of the work that we did was to try to understand the water on the and it's kind of interesting. You have four probably Nobel laureates on the one slide, Utrecht. So then the picture here is that on a protein surface, you have a water which is going in and out. So that exchange model, that water molecules cannot rotate. It cannot rotate if it is hydrogen bonded to a polar group in protein surface. It has to undergo a breaking of hydrogen bond in order to rotate. So this is the kind of water which is very slow and is responsible for the slow water molecules. And as I told you, there's a lot of on that controversy on that. These are dye molecules which were done, and then people have started metformin. I'm not going to go to that. But then again, going back to biomolecular water molecules that I said, is that the water molecules are constrained. And on the surface of DNA, protein, and in the groups of DNA, reverse micelles, lipid bilayer, the water molecules are constrained. The extended hydrogen bond of water gets compromised. Heterogeneous environment. But then it gives rise to huge amount of new phenomena, which now people are doing, trying to understand these properties of water. Okay. Now, this is the thing, as I said, we did a long time ago. The model is, if you want to read Biman Bagchi, 1997, when we did that model, which was now studied by many people, experimentally and theoretically, to see that water molecules. So there's a bulk water and there is surface water, and surface water is interacting with bulk water. So the surface water is undergoing certain kind of transitions to become bulk water, and water from bulk is coming and becoming a surface water. So all these extra dynamics that I'm saying in the left panel, all these extra dynamics takes place now, which are the fascinating new things and study of research now. And there is again a picture drawn by Amit Zuel, a little bit more science fiction kind of thing, that now showing the machinery inside, which is the protein helices and beta sheets and the water molecules on the surface. And in the bottom panel on the left shows that how water molecules undergoing a transition to become a free water molecule. So bound to surface water and free water transitions. So this is the study, huge study of protein hydration layer, which I'll not go any detail into that. There's a huge amount of study, as I told you, have been done in this field. From India, some amount of work has been done. It's the international one. There are everywhere people are working. One from is that Konkon Bhattacharya from cultivation did a lot of work on this. So, and as a result, there's a little caricature. There is a very famous poetry by Godfrey Sykes. Godfrey Sykes is 7 blind men of Hindustan. So the story is that the 6 blind men from Hindustan. So Godfrey Sykes' poetry goes like that there are 6 blind men who set out to, they argued how an elephant looks. Each has its own age, then so set out to find out by experiment how an elephant looks. And so one guy who touches the body says, oh, it's like a wall. One guy gets the tail, oh, it's like a rope. And one guy gets the leg, says it's like a trunk. So they all started quarreling and disputed loud and long, each in his own opinion, exceeding stiff and strong. Though each was partly in the right, all were in the wrong. This is a cartoon that we built, and is now many people are using a cartoon. Basically, what we tried to say, many different experimental that I did not go through. Many different experiments have been done. From the beginning, I told you the time scales were different, but there really a lot of controversy in the field. Which there is no reason for the controversy because each one, different experiments were giving different different results, and now we understand all these things. I think I have to go fast now. This is the Professor Amit Zuel. We did some very interesting experiments. He invited me once. I spent 2 months to. He did some very interesting experimental results. And my student is over enthusiastic by putting father of solvented molecules. No, I don't think he's a father of solvented molecules, but he has done amazing experiments. This is a very beautiful article. If you can get in from library, you would be able to get. Or if you don't, just ask me, I'll send you. Very long. There's all these beautiful pictures are there. And many of them, Professor Ahmed Zuel himself drew in his own hand. It's very nice. So, so then I think we went on trying to understand really how water molecules are different, why different experiments give different things, and what are the different region of time scales. Here on the right panel, lower panel, I show the protein. Then there are these 3 time scales. One is the water nearest to it, then next layer, then the bulk. And here is another one, that protein. And then you can, as you go towards bulk, the blue becomes deeper. On the protein surface, it is dynamical characteristics and its dielectric constant is low, like 40. Next, it becomes 45. These are each of these shell is about 1 nanometer. So you are talking of 10 angstrom. So about 10 angstrom, we can go subdivide further, but I'm not going to subdivide. To give you basic idea, broadly, please remember that on the surface, water molecules are slower and somewhat different. Then there's an intermediate, just like when you see from sky, water, you will see 3 colors. The water that is very close to the shore, near the land, that has a little bit between blue and gray color. Then you go a little deeper, you get kind of a light blue or light green color. Then you get deep. So exactly same thing happens in our calculations and in our theory. And then this is just one little thing on DNA. That DNA also, just like these are all protein. These are all protein. But here it is DNA also. Water plays a very important. And there are all these counter ions. DNA has the counter ions. It has a phosphate backbone. And phosphate backbone is negatively charged. And there is counter ions of the sodium. Typically 50% of the phosphate backbones are contain sodium. Other 50% is roughly is free. So, but they move around. So when you do dielectric luxation experiments or aqueous DNA solution, you get amazing results. Not fully understood, but still a very, very fascinating problem of DNA and water. Really, experiments were done by many person, but one of them is Usua. There is polyelectrolytes. There's a book by Usua, very famous scientist, very, very famous scientist. And then, but theory started now. Theory started, another series of experiments were done by Mark Bark. Theory started essentially after 2005 or 6. So you can see this is a really recent field. So these are more our metformin. We studied metformin, which is, main drug of diabetes. We first time studied the force field of metformin. We first time studied the dynamics of metformin and how metformin interacts with DNA. It has anti-cancer property. And Then I already talked to all these different water proteins, DNA, liquid, different from bulk water. One very interesting last thing I'll show that, insulin. Insulin is a protein, also called hormone. It's a polypeptide of 50, I think 52 amino acid long. Now, biologically active form of insulin is a monomer. That's what you need in your body. But when you are injected, it's a hexamer form. In a pancreas, insulin is stored as an hexamer. That's why any problem in pancreas, many times you either have a defective insulin, then a lot of difficulties. But a hexamer has to become dimer, and dimer has to dissociate into monomer. So here we have shown that a dimer becoming a monomer in the process, even when their center to center distance is 50 angstrom, 5 nanometer, surface to surface 30 angstrom, 32 actually. So 3 nanometer. Even then, water is very different from bulk water. And this is because of the charges and hydrophobic residues. Is a long story which is published in that paper of February. We have done a lot more work after that. And so these kind of raises the question. So the water can be considered confined water. How far then water knows? How far the effect of one surface goes to water, and there is one more surface, how far they interact? Water is such a small molecule, you think they will be by 10 nanometer, but I already told you in protein, no. And here I show you, they are apart, 30, 40 angstrom, still they are talking with each other, two proteins. It's amazing, it's beautiful. And then how far they apart two hydrophobic surfaces know each other. This has been a huge amount of work, huge amount of nature science papers, and all the other beautiful work that has happened. A lot of conferences going on this land. This is the point. And because this extensive hydrogen bond network of water that I discussed again and again, that is the reason why all these beautiful things happen. So one studying nanosphere, water within a sphere, one nano slabs, one in nano cylinder, one in nano tube, lots of things that is going on what now. And everywhere one finds the structure and properties of water inside this confined water is different. So confined water is a very different from bulk water. And for us, the confined water we must know, because there's so much water is in nature is under confinement. So this I already showed. This one more, so know each other. I think there is certain ions in water. I already talked to you a little bit that the ions behave very differently, and I already discussed this, that how they move. And so I end this now. Ions I could have talked a lot more, but it's already 1 hour over. And so I talked a little bit of the books that I want to. One is that many of the things that I talked today, not the latest one, is in my second book, which is Water in Biological and Chemical Processes. And then this one has become a different book with enlarged. INSA took a fancy of the book, how to perform well in academia. They have made it a different book. I'll show you a copy of the book, which is now it's called Vignettes for Success. This is I wrote for students, and it's a very I send it to your college, to Maharaj. So students should get, or I can ask. I'll send you the soft copies. The StatMag book I cannot, because I don't have the PDF. Other books I can send you the e-book or soft copy, and you can read that. And well, there are many other students, but there's two students. Pooja Banerjee's picture, I don't know how come it disappeared. Probably I wanted to give something better. So a good amount of it talk was prepared by Shomok and Sayantan. Sayantan is in Boston University now, and Shomok is going to leave for Germany soon. And Pooja is in University of Chicago. These are the three people who did much of the work. And insulin Puja Sayantan, confined liquid, mostly Sayantan. And many of these protein hydration layer water are Shomok and Sayantan. And many of the things, many of the slides are here made by Shomok. And this is the group. It's an old group now. Most of the people have disappeared. But here, fortunately, Puja is on the right extreme corner. Is Puja, okay. We at one time we really had, before the pandemic. At one point, we had a good group. Thank you very much for your attention, and please do read the books. And I think I'll stop here and take questions.
Thank you for introducing us to the amazing world of the water. And in a very short time, you have covered a wide range of subject areas. But I think we can now tell the students to ask.
Yeah, but my connection is very bad.
Yes, sir. Actually, I am also experiencing some problem in the network. Anybody wants to ask sir a few questions? Please ask.
I think, or they can aim. You should go over to Zoom. I believe Zoom has a much better connection than. See, you have to. One thing you have to be conscious of how much internet, like Microsoft Team. The problem of Microsoft Team is it requires tremendous amount of memory. Best is Google Meet, but Google Meet does not have a very good interface. Zoom is kind of a compromise between the two, and we like Zoom. We almost extensively use Zoom these days, and Google Meet. Google Meet is free.
Actually, sir, for our class purposes, we use mostly Google Meet, and the WebEx is bought by institute, so we have to use it, and it has some extra features.